Welcome to this pre-recording of lecture 6 of MCS 572. So today we are going to consider ideal parallel computations. One very prominent example of an ideal parallel computation are simulations. So while initially one could say the older term, the term I do not prefer to use, are embarrassingly parallel computations, but this has a negative pejorative connotation, and I prefer not to do this because ideal parallel computations are not trivial. So what is an ideal parallel computation? Well, all processes can run independently from each other and no communication needs to happen, except perhaps at the very beginning and at the very end. But in other words, there is no communication overhead. Would you then still need to care about this? Well, not everything is completely disconnected. So in the schematic here, we have 4 processors, starting the count always from 0. Every processor has an input and an output. We still work with the single program, multiple processors model, and there is one process that is going to distribute the initial input, and after the computation then all the results will be sent to the manager node, which will receive it. So last week in the previous 2 lectures we introduced MPI. So it was critical that for every send there was a matching receive. So here you see the 3 sends and the 3 matching receives in the diagram. So still this looks very straightforward, but there is still a problem of load balancing. So we will address load balancing in later lectures. So even though something can be without any communication overhead, one still has to make sure that all nodes terminate at the same time. So it could not be that one worker spends a lot more time than all the others, and that would prevent an optimal speedup. But in an ideal parallel computation, or also equivalently a pleasingly parallel computation, one may hope for an optimal speedup. Okay, so there are many examples actually that fit this category. So one has image processing, where one is going to compute a transformation of an image. One can, for example, improve the color encoding. So one has a big matrix of numbers representing an image, and all the pixels can be independently adjusted. So one can go from a red, green, blue color encoding to a grayscale, for example. And one can do all these computations in parallel independently. Now it's important here that this is not for distributed memory parallel processors, but on a distributed memory parallel processor, one would need to distribute the entire image over, one would need to scatter the matrix over all the nodes. And there the communication overhead would essentially dominate. So this is for shared memory parallel processors, or actually graphics processors. Another example is the computation of fractal images, so the Mandelbrot set. So one has an image where one where the image encodes the number of iterations that is needed to either converge or diverge. So one can take any root finder and consider, say, a polynomial with a number of finite roots, and one can draw a map given a starting value to which root is that position going to converge. So one can color code, so if one has three roots, one would have red, green, and blue, one could color the complex plane in those three colors. Also, everything can be done independently from each other. What we will do today are Monte Carlo simulations, because the simulations there require very little communication overhead, actually almost no communication overhead. So the point is that every processor generates a different random sequence, and that during this generation um, of the sequences, everything is happening independently. So a Monte Carlo simulation can still go horribly wrong when every process is generating the same sequence of numbers. And the same sequence could be identically the same, but it could be that there are kind of shifts in these sequences. So in some sense, Monte Carlo simulations are ideal parallel computations or pleasingly parallel computations, but they are not embarrassingly. So it's not really an embarrassment if you do not get it right. So there are things that can go wrong. Okay, so to make sure that we get the definition of a Monte Carlo simulation right. So here is a very simple example, an example that we also used in a previous lecture. So we want to estimate pi, which can be done by the area of a quarter of the unit circle, or one could, so here with the area of the unit disks, I took the integral from 0 to 1 of the square root of 1 minus x squared, so that's put me in the positive quadrant. So we generate random numbers between 0 and 1. So the random numbers will be uniformly distributed in the first quadrant. And we check for every randomly generated point whether it belongs to the circle. And that is counted as a success. So the number of successes over the total number of samples will approximate pi. So this is not a good method for pi, but for multi-dimensional integrals, and I will give examples of an application of that, Monte Carlo simulations are often the methods of choice for high-dimensional integrals. Okay, what is the point now? Well, this relies very critically that we can generate sequences of random numbers. And very, very long sequences of random numbers. So that is the nature of the problem here. In order for having a good accuracy, we need to take many, many, many samples. So, how do we do this on a computer? Well, there is the multiplicative congruential generator, a difficult word for a relatively easy computation. So, such a generator is determined by three constants, a multiplier, an additive constant, and a modulus. So we don't want overflow, so the numbers typically, so and typically this is also an integer computation, so that integer computation can be done with a 32-bit integer. So the modulus would be naturally 2 to the power 31 or less. Okay, so I should have said the whole point of this is that if you are using P processors, that you can do it P times faster. That's the optimal speed up. But there's also the quality up. If you can work with P processors, you can and work the same time, you would notice a more accurate result. So that's the notion of quality up. So one can see in the estimation of pi, if you take 10 times more samples, do you gain one extra decimal place in your estimate, which would be if you would be using 10 times more processors. So this is the assumption. This is also the hope for the optimal speed up. However, and here is where there are two problems. Your random number generators should first of all be all independent. So one needs to be careful about how one starts a sequence like this. So in some sense, a pseudo-random number is actually not entirely random. As soon as you fix the initial, the x naught here in the formula, as soon as you fix that number, everything is fixed. So they're actually not really a truly random number, because you know from the day you started, from the moment you start the sequence, you can actually predict any number in the sequence. You can calculate it. Okay, so one needs to make sure that one has sufficiently many different good starting points, because the choice of that seed will also determine the period. So you do not gain any accuracy anymore if you are starting to generate the same sequence of numbers. So there are repeated sequences. And of course, this is an optimization problem with constraints. So the random number generators are essentially always very simple formulas. So if you look at the number of arithmetical operations in this formula here, it can be evaluated very quickly. So this should be done fast. So that is a limitation. So one can come up with much better random numbers, but one has to be careful. It has to happen fast. Okay, so here are two pictures that I have copied and pasted from a paper by Anderson, published in the SIAM Review in 1990. So I will list the complete reference at the end of this presentation. These are two bad cases, so you see the patterns that are coming. So first of all, what does this plot mean? So we can look at pairs of random numbers, pairs of consecutive numbers. So if everything would be neatly randomly generated, as it should be, then one would expect that every dot appears in that square of 0, 1, but that is definitely not the case. So if one takes modulus M503, the additive constant is 0 and one has 62 for the multiplier, then you see that some patterns occur. So typically one uses prime numbers. So these first random number generators were constructed by in number theorists. So that's also the oldest technique. So the paper lists 5 common techniques. So there are 4 other techniques. So one can shift registers left and to the right to make random numbers. Other random number generators are what are called lagged Fibonacci generators. So I forgot here the modulus, but the Fibonacci numbers are obtained by adding the 2 last numbers in a sequence. Here you pick an R and an S, and you have to do the modulus operator, but instead of plus, you can also do subtraction, you can do multiplication. So there is some variation also here. One can start from a random sequence, 2 random sequences, and start shuffling them. So that's another way of generating more numbers. So at some point, one runs out of numbers, and one can start shuffling, and one can combine. So the combination is actually the fifth of the common techniques is actually a combination of the previous 4. So this is in a nutshell what one can do. And there are in statistics, by the way, many tests to check whether a sequence is truly random or not. Okay, so I am closing in on the half of this lecture. In this course, it's important that we do things. So there is software out there. I will present the Spring library. SPRNG stands for Scalable PseudoRandom Number Generators. So this is a package which is most likely already 20 years old, but it's still updated. So version 5 was updated to less than 2 years ago. I installed it today on my new M1 MacBook, and everything worked very fine. The default compilation uh, followed the quick start guide. So one can also then do the make install. So there is a website where you can download the software. I will illustrate the basic of the software, but there are a lot of tests there and a lot of checks and a lot of examples. Here is the check on the installation. So we include the header file. We use a very basic random number. So we are going to generate a random double. So here is the output, and the compilation depends on your installation. So if you work with the makefile, which I would recommend, then you would need to see where you installed it. So if you don't want to install, that is fine. Then you need to give the library the location where you compiled it for the include and for the libraries. So in the past, when I started using this, GMP was used, but in version 4, I've seen they actually wrote their own big numbers. So speed is definitely an issue here. One wants to really make sure that one uses the fastest algorithms out there that are needed for this purpose. So the GMP library is tailored towards exact, getting everything exact with large numbers. Here actually it's more speed that matters. So I can imagine what the motivation was for getting the proper, the optimized big number implementation. Okay, so in this hands-on demonstration, this is where the first bottleneck may occur, the installation. I would not expect any problem. Then the definition of the seed. So one can quite naively and quite so in last week when I also illustrated the Monte Carlo simulation, I was using the processor ID number as the seed. That seemed to be unique, and that might have been a good choice, but perhaps it might not. One has the advantage of using one of the uh, kind of standard libraries that some thought has gone into this generation of the seed. So the example program here will uh, return a different random double number. So I should say that I work also with a lot of random numbers when I test my programs, but that's different. So you just want some numbers. You don't really need this long sequences. Here is an idea for an initial seed. Most algorithms will work based on time, so that guarantees that every moment in time, so you have the year, the month, the day, the hour, the minute, and the second, essentially that every time you run the program, say in your lifespan, you will always see different numbers. So this formula here guarantees that you are within the 32-bit numbers. Okay, we crossed one hurdle. We installed the library. Let us now combine it with MPI. So we will estimate MPI, we will estimate pi with MPI, we will not estimate MPI. So here is a basic, first a sequential program. So we prompt the user for the number of samples. We initialize the seed. So we want that every sequence is different. We generate the random numbers in the upper quadrant, so the x and the y are generated in the um, positive quadrant, and then we compute whether we test whether the generated point lies within the unit circle. So in some sense, this is the algorithm. I like code in the sense that it gives us a unique and an unambiguous definition of the Monte Carlo algorithm to estimate pi. And it gives also a good check on the efficiency of the code. Here are some runs, to illustrate a little bit how bad this algorithm is. So in some sense, this is always a great candidate for parallel computing. So you can see here that that the accuracy actually does not really improve that much if you go from 100 to 10,000. There is some randomness there. So this is also on this slide here, I did 2 runs with 10,000, and you see that the second run happened to be better. Of course, in practice, I don't really know when I evaluate an integral what the exact answer will be. So you can see that this will converge rather slowly. So with 1 million samples, I get about 4 decimal places. Or not even 4. So if you round correctly, you have 3.141. Okay, let's improve this with MPI. With MPI, we used MPI CC. So now here we will have to use MPI C++, because the library is written in C++. So we include the MPI header. We ask for the number of processors, and we ask for every processor for its identification number. So the two last statements, so they get the ID, the identification number of each processor, and also the number of processors. Every processor will execute the estimate pi. So there is this int I that will be the ID number. So the parameter, the first parameter of estimate pi will be the identification number. And we have a number of samples. So the number of samples is prompted by the manager node. So we are working in an interactive environment. So the number of samples is broadcast. So that every worker knows the number of samples. So the number of samples remains fixed. So the computation is the calling of the estimate pi. Also the manager node, so the node with identification number 0, will also run the estimate pi. So the broadcast, and I use this program to introduce a new collective communication from MPI. So last time we have seen the MPI gather. Now we are doing the same as the gather, but we are summing the numbers. So there is one sum variable, and we have the sum variable that will be summed, so that will be the result. And every node has the variable estimate pi. So we pass the estimate pi and we pass it to the sum. So there are two locations. Perhaps I should go to the next slide. I tried to indicate this. So there is the estimate pi that is computed. So every processor, also processor 0, has this memory location. I called it now sums, but these are the sums of the successes. So every of the 4 processors has the variable estimate for pi, est4pi. Now in the gathering, one can use a gather operation so that every processor wrote to a specific location in sums, and then this gets gathered. But during the gathering, one can sum everything. So that is a reduction operation. So the 4 numbers are reduced to 1. So, and that is the final box at the top left. This is where at processor 0 will have the sum. So let me go back now to the previous slide. So sum is initialized here. So in some sense it's only, well, every node needs to have this, but that's a declaration. So every processor will have this sum, but actually only the root node, so that's the next to last argument of MPI reduced, where do we send everything? So that's the manager node with the identification number 0. Only the manager node will have the true value for sum. And that sum is then divided by the number of processors. So notice that here there will not be a speed up, but there may be, and we will actually expect a quality up. If you do this for 10 processors, you actually do 10 more samples because every process will actually do n samples. Okay, I should also show the syntax. So there is the um, collective communication that reduces data. So one can also have more than one number, but here we will do this only for one. It's possible to sum up and then also the receiver sum up different entries, and then the receiver also has different as many the receive buffer has to contain as many items as all the send buffers. It is possible to give other operations other than the sum. The product might be another, or you can have the minimum, the maximum. Um, so this is the reduction, which is a collective communication, and in some sense this is useful to overlap communication with computation, especially when you have a very large number of processors. All right, then we have the estimate function. So in the previous week, we had a very naive Monte Carlo where the processor ID was used for the um, for making the seed. So the seed was simply the processor ID, and that might not be so good, especially since there is also some repetition there in the sequence, possibly. Here, every processor will generate a seed. So this is where this SPRNG library is very good. So we will have almost for sure independent seed numbers. And then otherwise the function is the same as in the other code. It will actually print, so this is truly interactive. So every node will actually print its estimate and will actually also print the error on the estimate. Compilation, so I mentioned C++, so there is MPI CC, but there is also MPI C++. So one can use object-oriented programming. So here I give the syntax, the makefile syntax for on another Linux machine. The previous compilation instructions were for my M1 MacBook. So it depends where one installs the libraries. All right, I will end in the last 10 minutes with an application of a multi-dimensional integral. So this is called the mean time between failures problem. So I will give the sequential version. So as an exercise, it should not be too hard to come up with MPI version. So here is the problem. We have a composite product, and the product can consist of many components. So every component has an expected lifespan and a standard deviation. For this, it's very common to use the normal distribution. So that is another advantage here. I will illustrate how to build your own normal distribution. So there are here the respected means in the example 11, 12, and 13, and the standard deviations actually also go up. So naively one would expect that somehow the life expectancy is the minimum mean, but the variations and the standard deviations also play actually a role. In the Monte Carlo simulations, we don't see the integrals, but here is the formula for the mean of the composite, for the mean expected lifespan of the composite product. So this is a complicated integral just to look at. Now this is only for 3 components. Okay, how can you make a normal distribution from univariate, from uniformly random distributions? Well, one can look at the encyclopedia of Knut, and there is the Box-Muller method, which is in some sense, in a way, the difficulty with the subject here is not so much running the code or coding things up, but really making sure that the generated numbers can be considered normal. Okay, so here is then the function. So it requires it requires actually a lot more work. So you have to take the logarithm and the square root function. So in a way, one can kind of see that this implementation might not even be optimized, and it certainly isn't optimized, but this is the definition of the algorithm to generate normal numbers. So this is the Box-Muller method. Starting from 2 numbers, x and y here, uniformly generated. So what are all the stars doing in front of the letters x and y? Well, what happens is that we change x and y. So we start with 2 uniformly distributed numbers between 0 and 1, and we end up with 2 numbers that are normal distributed, normally with mean 0 and standard deviation 1. Okay, here is a check. So I coded this up, and I was using I'm using the properties of the good properties of the SPRNG library. So I'm generating my uniform numbers with that random number generator. And here is a test. So what counts as normal in the normal distribution? Well, it is, one could say, you're normal if you're like everybody else, but here you are normal if you are around 67%. So if you fall within the interval -1, 1, so standard deviation 1 of the mean 0, if 67 or 68% of the generated numbers fall within that interval. So this is a crude check to see whether we actually do have that property of our random numbers. The other more test would be to make a histogram, and then you should see the bell-shaped curve. If you are counting, if you are dividing your x-axis into bins, and then make a histogram of that. Okay, so this is a first test on our normal distribution. Now I had a standard. I have something that generates numbers according to the standard. Mean 0, standard deviation 1, but in my application I have 11, 12, and 13s as the mean. So I do need functions that are going to map any standard normal distribution to a normal distribution with a given mean and a given standard deviation. So that is what the map to normal does, and the map to normal is actually just a shift. So it takes longer to talk about it than takes to write about it. Okay, then the solution of our problem. So it's an interactive sequential program that runs this with 100,000 numbers. And you see, with 11, 12, and 13, we get a lifespan of 10. One can now wonder, what is the accuracy? Well, do many more runs and of increasing number of simulations. That's also the virtue of the random seed. You will see that the fluctuations, if the fluctuations are also kind of are also very good at telling. If you take, say, always the same number of simulations, the average will also be a good indicator how accurate things are. So that's another way of actually combining different runs. So I should say that these algorithms are also an example of the anytime algorithms. You can run these algorithms in batches of 100,000 and keep on running and averaging until you see that the average of the runs actually converges. That you see that at the end you have, for example, if you want 4 decimal places, you see that the 4 decimal places remain constants with the averaging process. Okay, there is the main function, the mean time between failures, that is going to compute the lifespan, the expected lifespan. And then there is the main function. So we can now put everything together. So we generate our normal numbers. So we essentially run so perhaps I should have said that this is quite general. So this is a composite product of m parts. So I coded this up with great generality. This also is apparent here with the number of components that is prompted for. Okay, one can turn this into a batch program very quickly, so that doesn't prompt the user for any input. Okay, so here you see the simulation. So what is done is that we compute the lifespan each time by computing the minimum. So we have 2 sequences of numbers. So the simulations are essentially ran in pairs. So, and each time when we generate, when we do another simulation, so for the m components, we sample for the expected lifespan, and the lifespan of the composite product is the minimum of all the lifespans. So here you see the consecutive minimums that we take. Okay, so there is an entire array, so that's the trouble here. So I see that we take n samples, and it's actually the entire array that is stored. So it's good for current computers who have no troubles getting very long arrays in memory. It's actually not such a good idea if you want to do this for a very, very long for millions and billions and trillions of simulations. So the memory will be quite bad. So that's another exercise. Do not use here but compute the sum as interleaved within the do loop. All right, I'm at the end, 5 minutes for time. I checked, so the SPRNG library has no Python interface and also no Julia interface. Not that I've been aware of, so I did not do an exhaustive search. Now, what do you do then when you have to use Python? So Python has a random number generator, but typically one generates numbers, random numbers in an entire batch. So NumPy can generate sequences rather quickly. So I would recommend to use the NumPy libraries. The random package in Julia seems to be quite well elaborated, and Julia is a fast uh, language geared towards high performance. I would expect that also there that could be a good starting point for looking at working with Monte Carlo simulations in Julia. All right, so I stolen some pictures in this lecture from the first reference, which is very readable. So SIME review, this paper has clearly withstood the test of time, still relevant. Then also the art of computer programming. Volume 2 is entirely has a significant portion uh, dedicated to random number generators. Then there is the you see I said that the library was already 20 years old, and here you see the original publication of this software. All right. Monte Carlo simulations are the prototype, or actually as the very first example of pleasingly parallel computations. These simulations are used very, very often, also on supercomputers. Um, so there are 3 exercises here. The first exercise kind of asks you to see the relationship between the error and the number of samples. One can see the speedup. One can experimentally determine the speedup. And then there is also using this SPRNG library. Okay, thank you for watching this pre-recording. I hope this was interesting. So we will continue our excursion in MPI. So today we saw the reduce operation. Later, when we go into dynamic load balancing, we will see the non-blocking point-to-point communications.